Hi there, in this video we're going to have a look at sketching the logarithm function, the base function really in this video, and in the second video we'll have a look at doing some transformations of the log function. So there's a starter here as you can see. So pause the video and have a go at rewrite. You don't have to solve them, just rewrite them. So you can see I've done it in the first one. So if y equals log 1, then that would be 10 to the power of y equals 1, because remember log base 10 is the base 10 is implied. So it's 10 to the power of y equals 1. So do the same thing for these ones and then we'll have a bit of a chat about it. Okay, hopefully you did pause the video. I'm just writing over to the side here, so excuse me if I'm a bit sideways to you. You should have got this. This would be 10 to the power of y is equal to 10. This would be 10 to the power of y equals 1,000. This would be 10 to the power of y equals 0.1. Bit boring, isn't it? 10 to the power of y equals 0.01. And 10 to the power of y equals negative 10. So that wasn't so bad. Now, if I did ask you to solve them, you could use way back last week, I think, when we were looking at, or at the start of the week when we were looking at exponential functions, you could solve them because all of those numbers there are really powers of 10. So you should be able to solve for y there. So pause the video and see if you can solve at least the first three. Okay, hopefully you did pause the video. 10 to the power of what equals 1? Well, 1 is 10 to the power of 0, right? So that means that y equals 0. 10 to the power of 1 equals 10, so y equals 1. 10 to the power of 3 is equal to 1,000, so y equals 3. 10 to the power of what equals 0.1, and can you do that without a calculator? The answer is yes, you can. I'm going to scroll down so that you can see this. 10 to the power of y equals 0.1, and 0.1 is 1/10. So that's equal to 10 to the power of negative 1, so y equals negative 1. 10 to the power of y equals 0.01 would be the same as 1 over 100th, if you know your base values. Sorry, your base decimal values, which is equal to 10 to the power of negative 2. So y equals negative 2, and so on. Okay. So that's some basic values there. And let's have a look at 10 to the power of y equals negative 10. Then again, we're trying to work out what value of y would I raise 10 to get a negative number, and the answer is you can't. So 10 to the power of y equals negative 10 does not exist for y. Okay, there's no value of y, it just doesn't exist. And it doesn't matter whether that was negative 10 or negative 1 or whatever else. So how does that correspond to a function? Well, the basic logarithmic function is going to be y is equal to log base a of x. Now, I've been using log base 10 because it's easy enough to deal with, but it could be log base anything, and the same sort of logic that I have here would work. But we need to consider what the domain and range might look like. So first things first, you can see that I can't put in a negative number into a log function because it doesn't make sense. It does not exist. And that means the domain is going to have to be greater than or equal to 0, or just greater than 0. Let's leave it at greater than 0, and we'll come back and put an equal sign there if we can prove it. So x would have to be greater than 0. We're going to assume a positive base. Now, you could have a fractional base. You can't have a negative base, and I've covered that in a different video. According to the documentation for Math Methods Foundation, we just have to worry about a being greater than 1, and that's how we're going to treat it in this year. So we're going to have a base, we're going to have an input, and then what kind of values can we get out of y? Is there any limitations to the values? We can already see that y can't be negative. Or can it? Yes, it can be. There it is there. Like so. So it can be negative. Can it be positive? Yeah, there's some positive values up here. So that's okay. It can be positive, can be negative, but are there any other limitations? Let's head over to Desmos and see what we can see. And I've started here by having some particular x values, and I'm going to plot the log of that x value. So that's log of 1. Unsurprisingly, it's at the coordinates 1, 0. So when x equals 1, the log of 1 is 0, because 10 to the power of 0 equals 1. Log of 2, there it is there, just a little bit further over. Okay, so 10 to the power of 0.301 would give me 2. Log of 3 would be 0.477. So just a little bit of a gap as well. It really feels like it's going to flatten out, isn't it? When's our next whole number? Well, 10 to the power of 0 is equal to 1. All right, okay. So we don't get to our next whole number until the log of 10, because the log of 10 would be 10 to the power of what equals 10? 10 to the power of 1. So 10 to the power of 0 is equal to 1 here, and then 10 to the power of 1. So there's 1 there, and we have to scroll, well, zoomed out a little bit, all the way out to here before we get to the next whole number. And then the next whole number will be at 100, because 10 cubed is equal to 100. Just think about those problems you worked out before for me. So there's the next one. Oops, that was probably not a good zoom. Oh yeah, that is. So we can see here that we've got 0, and then we get up to 1 here, and then all the way to 100 before we get to the next point up. Okay, I'll just show you what I mean by keeping it a little bit in perspective. There it is there. Okay, 1. And then I have to go all the way up to 100. Oh my gosh. To get to 2. And then where will I get to for the log of 1,000? That just gets me to 3, right? I'm going to zoom so we can sort of see it. Now, look at this. On the x-axis, it's scaled so that each of these little jumps here are worth 500 at a time. But each of the jumps here is just 1 unit at a time. So I've gone 1,000 units across for just 3 units up. So although it kind of looks steep here, in practice, it's because I've got differently scaled axes. What's happening really is it's flattening out. But here's the kicker. It's still growing. It's just growing slowly. And the more it grows, I won't do 10,000, but the more it grows this way, it rises only a little bit this way, but it still rises. So there's no limit to the y coordinates here. It's just that you'd have to get to extraordinarily large numbers to go much further up. But there's no limit. So there's no asymptote. Going in the opposite direction, so we've looked at positive numbers here. For positive, for fractions, you can see, that we're getting close to the y-axis here, but it's not on the y-axis. Let's have a look at the next one along, which is log of 0.01. It looks like it's on the y-axis, but if I zoom up, we can see that it's definitely not on the y-axis, but it's getting close. And the reason for that is kind of explained here, where you can see that we've at a tenth, at x equals 1/10, we get to y equals -1. And then if we just take a tenth of that again, we get to y equals -2. And if we took a tenth of that again, we get to y equals -3. And a tenth. So as we get closer and closer to 0, y is increasing but negative. And so this gives us our behavior here. Let me just zoom out a little bit. So let's see if I can fit. I'll do it in -10 to start with. So what's the log of -10? See if you can work out where the point goes. Nowhere. And that's because the log of -10 does not exist for this, because of this logic. Okay. Okay, so that last one doesn't really count. So if I zoom out, you can see that I've got this kind of behavior happening where if I go right to left, the points are getting closer and closer and closer to the y-axis, but not actually onto it. If I go left to right, they're moving away from the y-axis and are starting to spread out, but they're doing so in a way which is really, really quite flat. I know it doesn't look flat here, but remember the scales are different. So let's have a look at that in practice. There we go. It joins the dots, as you can see. So this is just the desmos of the function f of x equals log of x. And if I just get the scale back to regular, you can see how it's flattening out. And now if I zoom out, and remember this is all scaled, the x-axis and the y-axis are scaled, it feels like it's flattening out here, but it is flattening out, but it feels like it's reaching a limit, but it's not. As long as I go far enough in this direction, I'll keep on seeing a rise, and I'll continue to do so. In other words, I can solve the equation log of x equals 50. It's just going to be a huge number, that's all. I don't even know if the calculator will deal with it. So if I go log of, if I go solve log of x equals 50 with respect to x, whoa, 1.e50, which means 1, and then move the decimal place 50 times to the right. Actually, I could have figured that out, couldn't I? So that's a big number. That's bigger than a Googleplex. So we're talking big numbers here. It's often why you'll find that they talk about logarithmic scales graphs, and if you've been following anything to do with the pandemic over the last year and a half, then you might have noticed that a lot of their graphs that they show you are logarithmic in scale, just to make sure that they can be viewed properly, I suppose. There's more complex reasons than that, but that'll do. So this is the basic look at the function. Left to right, it's just going on forever, but just really slowly. Right to left, the graph is approaching the y-axis, so it's approaching y equals 0, but it's not actually ever reaching y equals 0. And so there is what is called a vertical asymptote at x equals 0. The y-axis is when x equals 0. Okay, so let's have a look at that, and we'll wrap up the video there. There's the base graph, like so. So on the base graph of y equals log base ax, we have an x-intercept at x equals 1, and we have a vertical asymptote at x equals 0, like I've got here. It steeply heads towards the y-axis as x decreases from 1 to 0. It slowly increases after x equals 1. And what else do I need to say? That's basically it. That's the graph. The other point I just wanted to make is maybe pause the video and think about it. Where is A? So A is greater than 1, so A is along here. Where's log base A of A going to be? Okay, so if you remember, log base A of A is equal to 1 from our log laws, which means that if I arbitrarily choose this as my point A, I'll do it in green, like so. This would be the point A. So if you remember from drawing graphs, I've suggested that you always find one other point to draw. Then drawing the point A, A would be an easy enough one to pencil in as your point of reference. Okay, I think this video has gone on long enough, so next video we'll have a look at some transformations.